So, in the last class we looked at the data of the ice cores and the incoming solar radiation, and we said that if the mean temperature of the polar region is linearly dependent upon the amount of radiation falling in the polar region, then we should expect that the dominant time periods of oscillation of the ice sheet should be dependent on the amplitude variation of the incoming radiation at 100,000, 41,000 and 20,000. The computations made by Milankovitch showed that the largest amplitude was occurring around 20,000, the precession cycle, but the observed dominant amplitude of the ice sheet based on delta O18 is at 100,000 during the last million years. So, we concluded that some nonlinear phenomena must affect the oscillation of the ice volume, because a linear theory is not working. It does not show the expected result. So, there is no simple explanation for why 100,000 years is the dominant period of the ice ages in the last million years. So, there is a transition from what happened between 5 million to 1 million and 1 million to today. Okay? This is known as the mid-Pleistocene transition. Now, in a recent paper, the authors say that the hysteresis loop of the North American ice sheet is such that after inserted ice sheet, its mass balance remains mostly positive through several precession cycles, whose amplitude decrease towards the eccentricity. As eccentricity goes down, you know that the effect of precession is somewhat damped out. Okay? So, the impact of precession is only good when there is a high eccentricity. Okay? So, their argument was that the 20,000 year cycle is not working well, because its radiation change is not sufficient to make changes in the ice sheets. Okay? So, this idea is of skipping, that is, because the maximum amount of incoming radiation is the 20,000 year cycle. If the ice sheet does not disappear every 20,000 years, this means that couple of cycles are skipped because of some other reason. Okay? Now, that reason is not clearly stated in this paper, and the reason could be that the carbon dioxide concentration was not sufficiently high to provide you the greenhouse effect to increase the temperature. That could be one reason. But the other reason could be also that, remember that ice sheets are very large, massive entities which have their own response time. Okay? And we will see later that when the large ice sheets were there in the northern hemisphere, in Canada, in Greenland and Eurasia, they actually had such a large weight that they actually depress the land by many 100 meters. So, the argument was, as the ice sheet grows, the land starts sinking. The land starts sinking, the ice sheet will melt because it will be at a lower altitude. Okay? So, that will slow down the increase in the ice sheet thickness, and the reverse will happen during the melting phase. When the ice melts, the land will start rebounding because there is ice sheet, and this will prevent ice sheet from melting further because the altitude of the land has increased. So, this is the factor which has not been accounted for by many people, which we will discuss a little later. Okay. So, this is the role of the what they call bedrock rebound. As the ice sheet grows, it depresses the bedrock and thereby increasing the temperature at the top of the ice sheet, thereby preventing the ice sheet from growing. And the other proposed nonlinear phenomena is the curling of the ice sheet margin. Remember that when the ice sheets grow, they come into the close to the ocean from the land and they start breaking off, calving. Okay. And that has its own time scale, okay, that operates on its own way, and it operates in a rather abrupt way. The ice breaking off from ice sheets has been observed in the last 50 years, and they are not linear phenomena, they are highly nonlinear. Okay. Some people also propose carbon dioxide variation and ocean feedback, but my concern is also dust feedback, because there is a lot of dust during the ice age. The problem with the last three, 0.3, 0.4 and 0.5 is that these are too fast. They occur over 5 to 10 year time scale. So, you cannot use this to explain the difference between 100,000, 40,000, 20,000 years. Those are very long time scale, these are very fast time scales. So, I would argue that only promising proposal is about the ice sheet depressing the land, because that is a slow process, because solid land is not going to respond immediately, there is a time lag of many thousand years. So, that can explain some of the unusual thing we see in the ice core data. So, typically a weight of 3 kilometer deep ice can depress the local bedrock by 1 kilometer. And there are two responses, there is an immediate response and there is a response with memory. For example, right now as the ice has been melting for the last 10,000 years, many parts of Eurasia are raising, because the ice is melting, land is rising. In parts of Sweden, parts of Russia, you look at harbors are having problems because the land is going up very slowly. Okay. So, this rising of the land is occurring now, although the ice sheet disappeared in those regions 10,000 years ago. Okay. That shows the lag, the late response of the land, and so that will affect any model that you use. Okay. So, bedrock has an elastic response and a delayed response. The elastic response is immediate, which is small, and the delayed response is large, but takes a long time. And that here has given us 3000 years. Okay. Some parts of Canada and Scandinavia are still rebounding from the last deglaciation. Okay. So, there are also some people concerned about the accuracy of the time in the ice core data. Now, that you may find it surprising, but you must remember that it is difficult to estimate accurately at what time the snow was deposited on the Antarctic region, and as it compacted and formed the ice layer, what is the exact date when that ice was formed, and that is very critical to understand these cycles. Okay. So, one proposal by Shackleton, a well known geologist, is that the 100,000 year cycle does not arise from ice sheet dynamics, as I indicated earlier, response of the land, but probably the response of global carbon cycle that generates eccentricity signal by causing changes in the CO2 concentration. My only problem with this paper is that the CO2 changes will occur at a much faster response time than the ice sheets. So, to understand the difference between 100,000 year cycle and 41,000 year cycle, to invoke the carbon cycle is a bit tough, because you have to talk about some other phenomena which makes the carbon cycle respond after many thousand years. Okay. So, that part has not been explained well by Shackleton. Now, remember that although Milankovitch mainly focused on solar radiation, but that solar radiation increase in the polar region will trigger other changes. Okay. One is it will increase carbon dioxide, methane and water vapor because of temperature rise, and that those gases will increase the greenhouse effect and cause further warming. This chain reaction called the positive feedback is very important for the ice melting. Same when ice becomes water, we all know that region will absorb 10 times more solar radiation than before. So, both these positive feedbacks will play a role in rapidly melting the ice sheet. But again, these feedbacks occur at a much faster time scale than the 100,000 year cycle. Although these are important to quantitatively calculate the temperature rise, it is not going to help us to understand the paradox that we saw in the last million years. So, let us look at what role has carbon dioxide and ice sheet albedo played in the feedback system. So, according to the models by Professor Jim Hansen from Goddard Institute of Space Studies, he has indicated that during the last ice age, on account of larger ice sheet and less vegetation, there was a negative minus 3.5, that is 3.5 watts per meter squared was a contribution of the ice increasing the albedo and cooling. This is the contribution to the cooling to the ice age, and greenhouse gases like carbon dioxide, methane, nitrous oxide contributed another 3 watts per meter squared. So, total of additional 6.5 watts per meter squared on top of whatever changes the incoming solar radiation had made. Okay. So, this shows that both the changes in greenhouse gases as well as changes in the albedo of the polar regions will play a role in the way the ice age collapses or the ice age accumulates. Both will be affected by these feedbacks. Now, there are some people who are arguing that Earth is a complex system and some of the forcing can be random, so called stochastic forcing. Okay. So, we can also think of this stochastic forcing may be due to a volcanic eruption, okay, which occurs at random. We cannot predict any specific periodicity for these volcanic eruption. So, they feel that on top of the smooth Milankovitch cycle variation of solar radiation, there was an additional stochastic forcing due to either volcanic eruption or some other cause. Okay. Now, this is an interesting hypothesis, but there is not enough data to support it. Okay. Now, the other important idea about the nonlinearity of the feedbacks during the ice ages is the idea of threshold. Okay. Remember that each time the solar radiation in the polar region decreases, you need not have an increase in ice volume, because there is a value of solar radiation. Unless it goes below that, ice will not form. Okay? Ice starts forming only when the temperature goes below 0. Suppose there is a polar region which is almost ice free, and the incoming radiation changed, let us say in the 100,000 year cycle, but the minimum radiation is such that it cannot initiate an ice age, then there will be no ice present. Okay? So, radiation is changing, but it is unable to trigger an ice age, because it is not below a certain threshold value. Okay? So, this is the threshold theory, that you cannot just only depend on changes in solar radiation, you also have to look at some absolute value of this radiation. Unless it goes below that value, ice will not form. So, this can be shown further with a cartoon. In a situation where the radiation falls below the threshold value, last time it did not, this time it does. Whenever it falls below threshold value, ice starts forming. Okay? So, the argument for this threshold hypothesis is that although the incoming solar radiation varies with a time scale of the dominant periodicity is 20,000 year cycle, but every time in the 20,000 year cycle the radiation may not go to sufficiently low value to trigger an ice age. Let us take this example. It started from a high value, it came to a low value, but still was above threshold. So, no ice formed. It decreased again and again it decreased, but again did not threshold, did not form ice. Then third time it went below, formed ice age. So, these are the two periods when Shackleton will say that the ice age is not triggered because it skipped, because the solar radiation did not fall below a certain glaciation threshold. Okay. The threshold hypothesis looks quite realistic, because depending on the other conditions in terms of carbon dioxide and water vapor, there will be radiation input which is to go below a certain value for the ice to start forming. Okay. It makes sense. Now, we go to a more dramatic case, so called the large phase, when the solar radiation falls such a low value that you will see ice forming almost every time. Okay. So, the idea is this periodicity of radiation is always there, but whether it will trigger an ice age depends on whether the lowest value of radiation does it go below the threshold value for that particular period, depending on this carbon dioxide, depending on methane, and depending upon the ocean circulation patterns. Okay. And here is one phase where the threshold is so high that all the time the incoming radiation promotes ice age, in which case ice will be there for a long time. Okay. This can also happen, and we will discuss this when we discuss snowball earth, which happened 600 million years ago, when under some unusual conditions the ice age grew all the way to the equator, and when that happened the earth was completely ice covered for millions of years. The incoming radiation change did not affect the ice cover, because it did not go below some threshold for those conditions. Okay. So, this threshold depends on other parameters in that period. It can be CO2, it can be methane, it can be the configuration of the land. The land configuration also has an impact. Whether land is in the tropics or in the polar region will affect. Okay. Now, this was taken up by people like Calder, who had a model. He said the rate of change of volume of the ice in the polar region is minus k, a constant, times I minus I 0. I 0 is a threshold value. So, in this model, unless I goes above I 0, volume will not increase. Okay. And notice that the value of k, the rate at which volume will increase, depends on accumulation and melting. It is not same. That is because ice accumulation, ice melting have a different characteristics. So, the k value has to be adjusted for the accumulation phase and adjusted for the melting phase. When he does that, he gets fluctuation of ice volume, okay, and he does a spectra. That spectra is able to pick up the 41,000 and 20,000 year cycle, but not the 100,000 year cycle. So, if you want to explain what happened in the period between 1 million years and 5 million years, you can invoke Calder's hypothesis. He will show you the peaks that occur in those periods, but you will not get the 100,000 year peak, which is what we observed during the last million years. So, the Calder's hypothesis works well for the period between 1 million and 3 million, but not between 0 and 1 million. Okay. So, that is the problem. Now, Imbrie and Imbrie proposed somewhat later a slightly different model, in which the rate of change of ice volume depends on whether the volume is above or below an equilibrium volume Vi. Okay. Vi is the equilibrium volume corresponding to some incoming radiation. So, if V is above Vi, that is ice volume is very high, then ice volume will start declining. However, as V is below Vi, it will start growing. So, that threshold value for ice volume is Vi, and that determines whether ice occur or not. And you can see that with that model Imbrie and Imbrie, we are able to get the 1,000 year, 100,000 year for all these cycles, okay, as per the data of the last million years. So, I would argue that the proposal by Imbrie and Imbrie that there is a threshold ice volume above which the ice volume will decrease, and if the volume of the ice is below the threshold, it will grow. Okay. And with that model, he was able to reproduce the observed cycle dominating at 100,000, 40,000, 20,000. So, many people are happy with this model of Imbrie and Imbrie, which was proposed more than 40 years ago. So, you can follow the logic of change in temperature proportional to ice volume, or you can talk about the ice volume depending on rainfall and temperature. So, there are various models proposed with threshold values which will determine the spectra of the ice volume. Now, this did not satisfy Salzman, who is a well known name in paleoclimatology. He has a book which is a very nice book. The Salzman and Marsh developed a model which is able to demonstrate the dominant 100,000 year cycle, and it is a nonlinear model. Looks like a nice idea, but it is not yet widely accepted. Okay. Now, let us see why. Let us say what the model is and why it is not accepted. So, model has 3 nonlinear differential equations. Okay. The first equation is for ice volume, the second equation is for T portion temperature, and the third equation is for carbon dioxide. So, Salzmann's argument essentially is that the ice volume does not just depend on the incoming radiation, which is here in his model f of y. It also depends upon the present temperature and the present concentration of CO2. So, he has coupled 3 nonlinear differential equations, and he gets, as you will see soon, a lot of good results, but he has not convinced everyone about the nature of these nonlinearities. Okay. So, that is the only problem. The nonlinearity that he has evoked is what you call ad hoc or empirical, and the proof from either climate models or actual observation is not yet convincing. Okay. But you can see that this paper published by Salzmann and Marsh is quite impressive, because black line here is the model of Salzmann and Sackmann, and the dotted line is the observed data from SPECMAC. And although there is no perfect agreement for the change in ice volume, I would argue that the broad peaks are matching quite well. Okay. So, I would say there is some merit in this model, because the oscillations of the delta O18 and the oscillation of the change in ice volume have broad agreements in the peaks. Okay. Not perfect, but broad agreements. So, there is some logic in Salzmann's thinking, but the concern many people have is that the nonlinearity introduced here, y squared, x squared, y squared and z, and sorry, only 3 nonlinearities here, they are not obtained from first principle derivation from any equation. So, it has been invoked empirically, because Salzmann realized that there has to be some nonlinearity. So, he introduced a simple nonlinear function, but we need to see whether these can be supported from climate models. Okay. Here is the example of ice mass and in this case carbon dioxide. Okay. The blue curve is the estimate of delta O18, okay, and the green is carbon dioxide from the ice core data. So, I would say that the Salzmann-Marsh model broadly reproduces the peaks in the ice volume and delta O18, the broad peaks, that is the 100,000 A peaks, but not the detail. Okay. So, I would say that this there is hope here that if further improve the model, we can get much closer match between the model observation. Now, we go on to understand how the ice ages are tipped due to volatility in the climate model. That is, there are equations invoke inequality, okay, that has to be addressed. So, I go back to my original equation of rate of change of temperature with here S by 4, sorry, S is incoming radiation, 1 minus albedo, which is the okay. So, this equation we have used many times before. So, we can look at it, but people in physics like to reformulate the equation in terms of a potential, okay, called the Lyapunov potential. You define the left hand side dt dt as a change in volume of ice with temperature. Okay. If you do that, then volume of ice integral becomes this velocity potential is defined this way through relationship temperature with time, and the velocity potential is the integral of this quantity, and this can be seen as follows. So, we saw this earlier also when we discussed the simple model, that between A and B the model is very unstable, there is no solution, while between B and C and below A the model is able to argue that these two states are more stable than this state. So, the argument is that the earth came out of the last glacial age due to change in sun geometry and some trigger posed by either volcanic forcing or factors which control the bedrocks. Okay. So, the idea is that the earth will go from glacial to non-glacial provided there is enough sun radiation and there is a trigger to push it to that other side. This trigger is very important because we will see later in the course that one of the major debates in the Paris Agreement was about the 2 degree limit. When the scientists proposed that we should not let the global mean temperature go beyond 2 degrees, the immediate reaction was, why 2 degrees? The answer was that looks like the threshold beyond which abrupt changes can occur. So, this is an example of abrupt change which we will discuss in some detail later, and so we need to understand what factors trigger this earth to go from a glacial state interglacial state through some non-linear phenomena. We will take this up in the next lecture. Thank you.